To the students, I would like to just ask you that, my intention is not to finish all my slides. So feel free to stop me because I can't see you. I don't know whether you can see me, but please raise your hands or, stop me so that we can discuss, we can communicate. The purpose of this school is to learn something rather than not telling you that how much I know or how much you should know that each other. Okay? So please stop me. So my life was very simple because you are already having lectures in this school by Professor Uma Shankar and Professor Vishnu Mukhopadhyay, and also Shirukda is going to teach, I think, or he has already taught, I believe. So they have already laid the foundation on which I'm going to talk about today. So you can see my title of this lecture is basically Present and Future of Neutrino Oscillations. And I would just like to give you a glimpse of what is happening now in this field and what we can expect, say in the next 10 years or so. Okay. So let me go to my first slide. If you will see that my slides are not changing, please stop me so that I can start again. So in this slide, we are discussing so much about neutrino oscillation, but the entire story started when we started, detecting these, invisible neutrinos. Now in this plot, you can see that, we have neutrinos in energy across 23 orders of magnitude. You can see in the x-axis, what is mentioned is the neutrino energy in electron volt unit. And in the y-axis, you can see the cross-section of electron anti-neutrino with electron in millibarn unit. So you can see if you start from extreme left to right, you have at the very extreme left very low energy relic neutrinos. We have not been able to detect them yet because we don't have that low energy telescope which will be sensitive to this kind of neutrinos. But then if we go towards right, we have neutrinos from sun, we have neutrinos from our Earth, then we have produced neutrinos in our reactors, then we have a supernova neutrinos, accelerator neutrinos that we have produced from pion and muon decay in our lab. And then around our atmosphere, we have atmospheric neutrinos. And towards the extreme right, you have very high energy astrophysical neutrinos. So I don't want to, tell you this. We all know that neutrinos are omnipresent, and we have been able to detect neutrinos from all possible these sources. And in this triangle, you can see the name of the experiments are mentioned. Okay, some of the experiments are future, some of the experiments are past, and some of the experiments are taking data now. So they all have a role when we say that we have detected neutrinos from these sources. Now, just to give an idea, the job was very difficult. You can see that when you increase energy, the electron elastic cross section, it is proportional to the energy of the neutrino. You can see on the bottom left, I am giving this expression. Now, if your neutrino energy is say 1 MeV, the area available for this interaction to happen is around 10 to the power minus 43 centimeters square. And if you go to 1 GeV, the area increases and the area is around 10 to the power minus 40 centimeters square. Now, we know that this cross section is plotted in millibarn unit, and 1 millibarn is 10 to the power minus 27 centimeters square. You can see on the top. Now, if you compare the area that is available for proton-proton collision at CERN, around 1 JF, the typical cross section is around 10 to the power minus 26 centimeters square. So you can immediately see that when you are talking about neutrinos, and especially their detection, their cross-section is 14 orders of magnitude less compared to the cross-section we see at CERN. So I think this can motivate that how challenging was the field to detect these neutrinos, but due to the development of human science and the progress, we have been able to detect these neutrinos, and that's why we have been able to, measure some of their interesting properties. So the message that you should take, that if you study about neutrinos, they help you to learn about fundamental science across an energy which is belonging around 23 orders of magnitude. And that is very important. Now let me go to my next slide. So I told you that, we have a nice panorama or landscape of neutrinos where, we have roughly, 18 orders in energy. Here I'm talking about the energy range where we have detected these neutrinos, and also 25 orders in length scale. So in this plot, in the top plot, you can see in the x-axis, you have neutrino energy. And in the y-axis, you have the distance traveled by these neutrinos. So can you see that when you think about the distance that neutrinos travel from various sources before they reach to you, that distance is in the range of from few kilometers to say gigaparsec, which is close to the ZZK horizon, or even at the extreme boundary of our observable universe. So in the left, you can see that, we have mentioned this reactor, geoneutrinos, solar neutrinos, supernovae, and this VSLBL is very short baseline oscillation experiments, and this SBL stands for short baseline experiments, and this LBL stands for long baseline oscillation experiments, where you basically throw a neutrino beam from your lab and you put some detector at a certain distance and you observe some phenomena. And then you have atmospheric neutrinos. So you can see in this pink band, this is the range of energies where we have been able to detect neutrinos today, and we have tested their properties. And if you go towards right, in this cyan band, we expect that, we'll be able to see neutrinos in coming years, thanks to the big neutrino telescopes like IceCube or Chem3Net in Mediterranean Sea, or IceCube Generation 2 or future upgrade of IceCube. We hope that those telescopes will also be able to detect neutrinos at these very high energies. Okay, so the summary is that we have made remarkable progress. We have been able to detect neutrinos from various sources having different energy and distance scales. And I must admit that the detection of cosmic neutrinos, especially the neutrinos from sun and supernovae, they opened a new window onto the universe. We are learning about those far-reaching objects via these neutrinos. And in 2002, when the Nobel Prize was given to Raymond Davis Jr. for detecting solar neutrinos and Posiba-san for detecting supernova neutrinos, the era of neutrino astronomy began. So, this is really amazing that, just 20 years back, we could detect neutrinos from these sources and Nobel Prize was given. Okay, so let me proceed further. So again, you see in my next slide, this slide, on the top, I have the same figure. But when we talk about neutrino oscillation, which is the theme of my talk, so when neutrinos are produced from some source, neutrinos are produced in the flavor state, or we can say weak eigenstate. And when you detect neutrinos, they are also in the same weak eigenstate or flavor state. And we call them like, electron neutrino or muon neutrino or tau neutrino. But some funny thing happens when they travel. These neutrinos, they are weak eigenstate or flavor eigenstate, do not coincide with the mass eigenstate. So when neutrinos propagate through medium from source to detector, they propagate in mass basis. And when you allow these neutrinos to travel, they change their flavor. This is what we know as neutrino oscillation. And thanks to these experiments, which I have mentioned in the boxes, the solar neutrinos, neutrinos from our atmosphere, neutrinos from reactors, where from we get electricity, and lab-based accelerator neutrinos, when we have studied them, they have firmly established one phenomena, which is which is known as neutrino flavor oscillation. This is the mass-induced neutrino flavor oscillation. I want to emphasize this flavor transformation is happening, which is induced by mass. So it implies that neutrinos are massive and they should mix with each other. Now, I will not discuss this, but I think it has been covered in this school nicely, that in the basic standard model of particle physics that we have, neutrinos are massless. Because what we have seen in nature, all these neutrinos are left-handed and anti-neutrinos are right-handed. But in the basic standard model picture, when you want to give mass to a particle, you need both left-handed guys and right-handed guys. So in that prescription, we can't write the mass term for neutrinos. So the theory suggests that they should be massless. But as I told you, we have plethora of data from these various experiments, and they are suggesting that neutrinos do change their flavor, so they should have some mass. So you see immediately there is a contradiction between theory and what your experiment is telling you. So if you believe in your data, and which you should, because I will convince you in my talk that this is just not a 2 sigma, 3 sigma hint, rather, this is, now we know that neutrinos oscillate on a very firm footing. And I will convince you that this model of neutrino oscillation is very simple, but at the same time, very robust. So if we need to explain the data, we need to extend our standard model, the picture, that basic standard model of particle physics, and we need physics beyond the standard model. Why? To explain this non-zero neutrino mass and mixing, that you need to explain neutrino oscillation. And I feel very happy to say that this is the first experimental proof of physics beyond the standard model. And for this, 2015 Nobel Prize, was given to Professor Kajita-san for detecting neutrino oscillation in Super Kamiokande experiment, and to Professor Arthur MacDonald for detecting, solar neutrinos in Sudbury Neutrino Observatory. Okay, so now let me move to my next slide. So in last 23 years or so, we are living in a golden era of neutrino oscillation physics. There is no doubt. So here you can see in the top left, we have the neutrinos from sun. And I have mentioned, I will not read the name of the various experiments which have contributed to this field. Then we have neutrinos from reactors, rather electron anti-neutrino. And from the sun, we have electron neutrino. Then we have our atmosphere. And there the main candidates are the Super Kamiokande, the standard candle for neutrino oscillation physics. And then ice cube and big four in last 5-6 years, they are also contributing in the field of neutrino oscillation science. And at the extreme right, I have neutrinos from accelerators. Basically K2K, it is already over. MINOS, this is also over. T2K and NOVA, I will talk about them. They are currently taking data. But all these experiments have contributed to what I'm going to talk about today. So you see, we have solar neutrinos. In atmosphere, we have both muon flavor and electron flavor neutrinos and anti-neutrinos. And in accelerator, we produce a muon flavor neutrino or muon flavor anti-neutrino. So when we gather data from these various neutrino sources, I would like to ask you, basically students, to appreciate one thing. If you think about these sources, they are vastly different in nature from one another, right? When you are talking about sun, or I'm talking about atmosphere or reactor or accelerator, the energy of these neutrinos are totally different. The length scale that they travel before reaching to a detector is also different. The systematics of these experiments are completely different. The whole, experimental technique that we adopt in these experiments are also different. But all these experiments are pointing towards one beautiful thing, that if you allow neutrinos to travel, they will change their flavor. And I must admit that we have just started our journey, and we have a lot of things to explore in near future. Okay, so let me proceed. So I will very briefly discuss the simple and robust three-flavor neutrino oscillation framework. I'm sure Professor Umashankar, from whom I have learned the basic of neutrino oscillation physics, he has taught you about this, but I will just very briefly, just point towards some important points. So you see in this slide, in the left, you have the flavored neutrinos, nu e, nu mu, and nu tau. And in the right, you have the mass basis, the mass eigenstates of neutrinos, nu 1, nu 2, nu 3. Now I told you, for neutrinos, their flavor eigenstates do not coincide with the mass eigenstate, but you can connect them. You can connect them using a nice 3 cos 3 unitary matrix. Basically, you have 3 Euler rotations you can think of. So at the extreme left, you have rotation around 2, 3 axes, which we call the atmospheric mixing angle, theta 2, 3. Now, we have learned about this mixing angle by exploring atmospheric neutrinos and neutrinos from our accelerator beam. At the extreme right, you have theta 1, 2. So this is the rotation around 1, 2 axis. So this is in literature known as solar mixing angle. And we have learned about this mixing angle by studying solar neutrinos, as name suggests, and from neutrino and electron antineutrinos from reactors. Now, at the middle, we have the last piece, which was unknown, which is the smallest lepton mixing angle, and it was unknown till 2012. Thanks to Diabe, they announced the discovery of non-zero theta 1, 3 in 2012. You can see in the middle. And also later on, T2K also confirmed that they have seen theta 1, 3 driven nu mu to nu e appearance in their detector. And you will be surprised to know, though theta 1, 3 started its journey very late, but if you see now, theta 1, 3 is the most precise mixing angle that we know. So we have 3 mixing angles. Now you can see, since we are working in a 3-flavor paradigm, because all these 3 mixing angles are finite, then the model allows you to incorporate a CP violating Dirac phase, which we know as delta CP. Because you know that if you want to parameterize a 3 cross 3 unitary matrix, you need 3 real variables and 1 complex variable. So these 3 mixing angles are their real quantities, and this phase is basically denotes the complex part. So what are these mixing angles? When I say theta 1, 2, okay. So when you write down the matrix elements of this 3 cross 3 matrix, you have UE1, UE2, UE3. What is UE2? UE2 tells you that how much nu e is there in the nu 2 mass eigenstate. And what is UE1? It tells you that how much nu e is there in the nu 1 mass eigenstate. And remember, guys, these quantities are fixed in nature. Whatever parameterization you take, okay, what we measure in experiment is this quantity, that how much nu e you have in nu 2 mass eigenstate or how much nu e you have in nu 1 mass eigenstate. And ratio of these two quantities squared tells you, gives you the theta 1, 2 mixing angle in this parameterization. Similarly, the ratio of u mu 3 square over tau 3 square gives you theta 2, 3. And you have this theta 1, 3. This is the reactor mixing angle. Now, since you are in 3 flavor, you can accommodate this delta CP phase. So you can see that the importance of θ13 is huge. If θ13 would have been 0, then we are not anymore in three flavor paradigm, and you will not be able to invoke this delta Cp in your picture. So there will be no Cp violation. But we are lucky, we have seen evidence of non-zero θ13 at very high confidence level. So now there is a possibility that we can invoke a delta Cp phase, and the role or the goal of the next current and next generation oscillation experiment will be to measure precisely the value of this delta Cp phase. We need to establish that the value of this phase is neither 0 nor pi, so that we can tell with unprecedented confidence level that we have seen Cp violation in neutral lepton sector dealing with neutrinos, and it has its own far-reaching consequences. If we can establish Cp violation in neutrino sector, that will guide us to develop models or theories which may explain the observed matter-antimatter asymmetry in our universe. So what is there in this model? To make a summary, we have three mixing angles. We have one Cp violating Dirac phase, and in particle physics, we are familiar with wave-particle duality. So sometimes you can consider neutrinos as particles, sometimes they behave like wave, and the mass of the particle will give you the frequency of the oscillation of that neutrino wave. So we have in three flavor picture, two independent frequencies. One is known as atmospheric frequency. I hope you can see my cursor. And its value is around 10 to the power minus 3 eV squared. This is the mass square difference of third mass eigenstate and the first mass eigenstate. And in the right, you have the solar mass square difference, which is around 10 to the power minus 5 eV squared. We have measured their value quite precisely. Okay. And if you see, the atmospheric mass splitting is almost 30 times bigger than the solar mass splitting. But here I have just written the simple two flavor neutrino oscillation probability expression. This is telling you that what is the probability if you start with the flavor alpha of neutrino, it will oscillate to beta. And this is nothing but a very simple product of two sine square function. And what is there? You have the theta, the mixing angle I just explained to you, and you have the delta Mij square, the mass square differences, which governs the frequency of the oscillation. And this L is the distance that neutrinos travel, and E is the energy of the neutrino. So you can see here that if you want to probe a value of delta M square around 2.5 10 to the power minus 3 eV squared, you need an L by E around 500 kilometer over GeV. So that immediately tells you what are the experiments that are going to give information about this atmospheric mass splitting. Whenever you will see that you have a neutrino and the ratio of its baseline over energy is around 500 kilometer per over GeV, they are certainly going to contribute in this study. But when you are looking for a solar mass square difference, if you see in this formula, if you put some value around 10 to the power minus 5 eV square, then I told you that it is roughly 30 times smaller. So you need 30 times bigger L by E value. So you need around 15,000 kilometer over GeV. What I'm explaining, these are the nutshell. These are the most important thing of this basic simple picture of neutrino oscillation. So if you encounter neutrinos whose length over energy is around 1,500,000 kilometer per G over GeV, they are also going to contribute to measure this solar mass square difference. So here at the below, I have written the full three flavor neutrino oscillation probability expression. And you see here, if you see my cursor, this tells you this is the real part of the mixing matrix and this is the imaginary part. And this will come into the picture if delta Cp is non-zero. So And this is the expression for neutrinos. And if you want to write down for antineutrinos, U will become U star. That means delta Cp will go to minus delta C. So this is the summary, that in simple 3-flavor picture, we have 3 mixing angles, 1 Cp phase and 2 independent mass square differences. Okay. Now let us complicate our life little bit more. I just told that things are simple, but now things are not any more simple. When you look at these sources, and when these neutrinos travel from source to detector, they don't travel, most of the time in vacuum. They also travel through medium. And when neutrino propagates through matter, that propagation can disturb your oscillation phenomena. Rather, that can modify your oscillation phenomena. So when neutrinos are traveling through matter, they can experience a coherent forward elastic scattering with the ambient matter particles. Now, when I say ambient matter particles, you have electrons, protons, or neutrons in the matter, right? Now think about when a nu is passing through that matter, nu can have both neutral current and charge current interaction with electron. Here in the right, I am showing the Feynman diagram, which is responsible for the charge current interaction. You see, this is a W mediated process, okay, between electron, neutrino, and electron, okay. But this nu can also have neutral current interaction with electron, proton, and neutron. But when you come to nu mu or nu tau, they will have only neutral current interactions, okay, with electron, proton, or neutron. So when you want to take this effect into account in your oscillation probability, since the neutral current contribution is flavor blind, they will not affect your oscillation or transition probability. Only the charge current contribution, which is coming through nu E scattering or nu E scattering, that is only going to affect your oscillation probability. And how does that term look like? So this is known as Wolfenstein matter term, and this is proportional to the energy of the neutrino and the electron density that you have inside the matter, and GF is the Fermi coupling constant, and you have some constant value over there. Now this potential is positive for neutrino and negative for antineutrino. By the way, I want to mention that if you can probe neutrino oscillation, then you also become sensitive to this Ne, right? What is the density inside the electron? And I will flash some practical application of this neutrino oscillation phenomena towards the end of my talk, if time permits. So you can write down this potential in terms of the density of the matter and the energy. Now, you can immediately understand that due to the presence of matter, it will switch or change the sign when you go from neutrino to antineutrino. Now, think a situation. You have produced a neutrino beam in your lab and an antineutrino beam in your lab at different times, and you are shooting that beam to your detector. Now, if you study the oscillation probability of those neutrinos and antineutrinos separately, and suppose if this Cp phase that I have been talking about, if it is really zero in nature, then also you will see that these two probabilities are not same. Why? Because there is one difference you have initiated. That is because of matter. So the take-home message is that even if your delta Cp is zero in nature, the term that helps us to measure the Cp asymmetry, that is going to be finite because you have matter. So you can say that matter brings in the fake Cp asymmetry. And this is a very important point that we should understand, because the biggest challenge the current and future experiments are going to face is how to disentangle between fake Cp asymmetry and the genuine Cp asymmetry that you can have due to non-zero values of delta Cp phase. And it is very complicated. It's a very complicated study. if you want to disentangle these two effects in same experiment from the same data set. Okay, you need multiple experiments at various energies and various baselines, and you need to also probe various oscillation channels if you want to disentangle this effect. Okay, now you can immediately see that if your atmospheric mass square difference turns out to be at the same strength of this matter potential, then inside the earth you can feel resonant conversion. What does that mean? So if you encounter this situation, then if your θ13 to begin with very small number, I will flash that number. The present global field study tells you that the value of θ13 is around 8.6 degree or so. But when neutrinos are traveling in earth matter, then this θ13 can attain a value of maximal mixing, which is 45 degree. And this is known as Msw Resonance. And this can happen if your neutrinos will have energies around 6 to 8 GeV. And if you allow these neutrinos to travel a distance of around 6,000 to 8,000 kilometers inside the earth. Now you can see on the left hand side, this equation will be valid. Okay, you will encounter this situation if the sign of these two quantities are both positive or negative. Now I told you just few minutes back that this A is positive for neutrino. Now I will tell you that we don't know from the present data that what is the sign of atmospheric mass square difference, whether M3 is heavier than M1 or M3 is lighter than M1. And this is known as neutrino mass ordering problem. Now, if in nature, this atmospheric mass splitting is positive, and if you are dealing with neutrinos, then this A is also positive, and you will see this resonant conversion. On the other hand, if this ordering turns out to be inverted, and if you are dealing with anti-neutrinos, then this A is also negative, and you can encounter this kind of resonant conversion. So these are very important things when we would like to analyze our oscillation data. These informations are very important, and so try to understand, and this will really help when we will analyze our oscillation data in next few slides. Okay, so let me quickly tell you what are the open questions we have. I just told you that present data tells us that this M2 mass eigenstate is heavier than M1 mass eigenstate. How? By exploiting the solar oscillation data and the energy dependence of little bit higher energy solar neutrinos where they feel matter effect, we could nail down that delta M21 square, the solar frequency, its magnitude as well as its sign. That means we know that M2 is heavier than M1. But we really don't know from the present data. We have hints that whether M3 is heavier than M1 or lighter than M1. So the question is, neutrino mass spectrum can be normal or inverted. But you should realize one point, that from this cartoon, we already have a lower bound on the mass of heaviest neutrino. How? You can see, suppose you take this normal picture, okay, and you don't know basically that whether this is heavier or lighter than M1, but you know the gap between them quite precisely. So you can say that since you have a lower bound on the mass of the heaviest neutrino, because if you just make it 0, then you can tell that where your M3 lies basically, okay, what is the distance between these two. So that will be your lower bound on the mass of the heaviest neutrino, which we don't know which one is the heaviest, but we have a lower bound on the mass of the heaviest neutrino, because we know that this splitting between M3 and M1 is around 2.5 10 to the power minus 3 V square. So if you just assume that your solar splitting is 0, then you can just, or if you assume, you can't assume solar splitting to be 0, let me just correct my statement. If you can assume, because you don't know where M1, M2 and M3 belongs. So if you assume that your starting scale is 0, that means M1 is at 0, then you can assign the total gap to M3. That means you are getting a lower bound on the heaviest mass state, and which is around 0.05 electron volt. Okay. So I want to just point out here that the nu-E component of nu1 is heavier than the nu-E component of nu2, which you can see from here, and nu-E component of nu3. But this issue of mass ordering is a binary type question, right? Once you discover that your mass ordering is normal, you are fine, or it is inverted. There is no picture lies in between. So this is like a yes or no type question. And I want to emphasize that we need to probe this quantity, we need to measure this issue, or we need to settle this issue, because this is very important when you want to build the neutrino mass models. Okay, this neutrino mass ordering will serve as a crucial input. Okay, and you need to know beforehand when you start building your model that whether your neutrino spectrum is normal or invertedly ordered. Okay, so that will be a very crucial input. And also, depending on whether neutrinos are normally ordered or invertedly ordered, your data will be affected a lot, especially when you have matter effect. Okay, that I am going to discuss in my next slides. Yes.
Professor Agarwalla, one moment. There is a question from Dwaipayan Mukherjee. Dwaipayan, sure. Please unmute yourself and you can ask the question.
Okay. Hello, sir. Can you hear me?
Yes.
So my question is regarding the MSW effect. So apart from electron contribution, there must be contributions from protons and neutrons as well, right?
Yes.
Okay. So, sir, from this, what can we infer about the extreme nuclear physics that is going on, say, in astrophysical objects such as supernovae or these extreme objects from these neutrino oscillations?
Yeah. So definitely, when neutrinos are passing through matter, they can also reveal the information about the matter content and all. I will talk about that. But first, I want to clarify one thing, that as far as neutrino oscillations are concerned, the only thing that matters is the interaction between electron, neutrino, and electron. Because you need to understand that your matter is not CP symmetric. You have only electrons in the matter, not positrons, or you don't have muon or tau in the matter. So whatever interaction is happening with proton and neutron with nu-E or nu-mu or nu-tau, they will be all neutral current type and their strength will be same. Okay, so this interaction will be flavor bind, and then you can just take this out from your oscillation expression as a common phase, and they are not going to affect your oscillation phenomena that we are talking now. Okay, but indeed you can really tell that what amount of electron these neutrinos has felt on its way, whether you are in CERN or whether you are in supernovae or whether you are inside the earth, whatever.
Okay, thank you.
There is one more question in the chat box by Sabila Parvin.
Yes.
She says, could you please repeat again the lower bound of mass?
Yes. Yes, Sabina. So let me explain to you. Can you see my picture on the present slide at the left hand side? Yes, sir. So just look at the left hand. You imagine that neutrinos are normally ordered. Okay, just as an example. So what I told you, that present data tells you that what is the gap between the M1 and M2 mass eigenstates, and also it tells you that M2 is heavier than M1. Clear? Also the present data tells you that what is the gap between M1 mass eigenstate and M3 mass eigenstate, but the data do not reveal whether this M3 mass eigenstate is heavier than M1 or lighter than M1, right? That's why these two possibilities are coming. But you need to understand, we just know the gap, but we don't know the mass of the lightest neutrino. Suppose in this picture, which one is lightest? M1, right? and you don't know that. Now, if you assume that my M1 is 0, then your delta M31 square, which is M3 square minus M1 square. Now, M1 square is 0. So this delta M31 square is nothing but M3 square, right? So in this picture, M3 is my heaviest neutrino. And my starting point, M1 is, I'm assuming 0. So you immediately see that the mod of delta M31 square, the magnitude, is nothing but equal to M3 square, because M1 square is 0. So if you just take the square root, which I have taken, you will get to know that what is the value of M3, right? 0.05 EV. Now you can say, no, I want to give some mass to M1. So then you will push this up, right? This value. When you will give some mass to M1, M3 will also go up. That's why I'm telling that we only have a lower bound, right? You know that M3 can't be below than this, but it can be above on this value. And what is that value? Is 0.05 electron volt. Sabina, is that clear to you?
Yes, sir.
Should I proceed?
There is a third question from Gautam.
Yes.
Gautam, please, if you briefly ask your question.
Hey, Professor, can you hear me?
Yeah.
Okay. Yeah, I was wondering, is it not possible to get more constraints for neutrino masses from like cosmological sources or limits?
Yeah, if I understood your question, you are talking about cosmological connection with neutrinos, the mass?
Yes, sir.
Yes, very good question. This is beyond the scope of my talk, but I can tell you certainly how heavy the neutrinos are. That is going to affect your, Big Bang nucleosynthesis process a lot, the BBN era. Okay, so certainly the Planck experiment has said that the most tightest bound on the sum of the 3 light active neutrinos, okay, and which is now below electron volt, like 0.2 eV. The sum is below 0.2 eV, even 0.15 eV. So yes, more mass means more radiation. So cosmology can tell you how many light species are there if you reach the equilibrium, basically, if you have achieved the equilibrium, and what is their masses. So you are absolutely correct.
Okay, and this works with all cosmological timescales, or are there some models which predict that the neutrino might be younger than the universe? Because I'd assume that would affect.
I didn't understand, Gautam.
Yeah, sorry. Yeah, I feel like I'm breaking up. Yeah, no, my question was, does this prediction bound on the sum of neutrino masses hold for all cosmological timescales, or are there some limits on that as well?
Yeah, see, so when you see the data, basically you integrate over all the length scale, right, or time scale, basically. But right, mostly the effect comes from BBN, as far as my understanding goes.
Okay.
And but again, I am telling you that what is the sum of the neutrino masses, or how many light species are there? If you believe in standard candle of cosmology, the lambda CDM model, then they are tightly constrained. Okay. But there are always loopholes, right? We are all BSM people. Right. So you can always cook up some interesting models. And I am not saying that they are just, they have meaning, okay? You have meaning to build some models. And if you believe in those models, then you can, loosen these constraints on light neutrino masses of the light neutrinos and the number. Okay.
Okay, great. Thank you. Thank you, Professor.
Yeah. Adindam, should I proceed? Hello?
Hello.
Adindam, should I proceed?
There are 2 more questions in the chat box.
Yeah, sure.
Okay, you would like to take them now? Okay.
Yes,
so
yes.
One from Prantik Sharma. From
Prantik,
which?
Bolo.
Prantik, you may also unmute yourself and I ask the question.
Oh. Yes, sir.
Yeah.
Can you hear me?
Yes, Prantik.
Yes, so I was I wanted to know, from which experiment this lower bound on neutrino mass was, heaviest mass was obtained.
Okay, so see, for this you need many information. You need to know what is the gap between M1 and M3. So I will just tell you that I told you already, the magnitude of delta M31 square, that the gap between M1 and M3 we know about this quantity from atmospheric oscillation experiment and long baseline neutrino oscillation experiment. Okay, they have measured this quantity very precisely, that what is the gap between M1 and M3. Okay, so I must tell you that that number I am only using, right, to put the lower
Yes.
bound on the heaviest state. So the credit goes to atmospheric experiments and long baseline experiments. I am going to talk about them.
Okay, sir. Thank you.
Okay. Any more question?
There is another one from Sushavan. Sushavan, would you
Yes, Shushaban, tell me.
like to ask this?
Am I
Yes.
audible, sir?
Yes.
Thank you. So, the standard model of particle physics table, which we are very familiar, where all the leptons and quarks are arranged generation-wise, there we can see that the upper bound of the masses of these three neutrinos are written rather than lower bound. Like electron type neutrino is less than 1 electron volt, tau 1 type neutrino is less than 18 mega electron volt, like this. So my question is how the upper bound limit is being determined.
So, those numbers are written in that picture, if you have seen that basic standard model picture, but those numbers are not exactly correct. First of all, you need to understand that when you mentioned that three generations are nicely arranged, if you think about, the charge leptons, electron, muon, and tau, for them, your flavor eigenstate coincides with the mass eigenstate. The kind of experiments we have, that is the phenomena that we can rely on. So they are, the flavor and mass, basically they are same because they coincide. So you can write that I have this much muon mass, this is the mass of a muon, this is the mass of a tau, this is the mass of electron. But now I just explained that for neutrino, when you produce or you detect, then they are in the flavor basis, but they propagate in the mass basis. So I must say that when you think about this mass, you know that this flavor eigenstate is the linear superposition of mass eigenstate. So there is a catch when you say that mass of the electron neutrino. What we only know, as I told you again, that from cosmology measurement, we just know that the sum of the three light active neutrinos, nu e, nu mu, nu tau. I say light because there can be some heavier neutrinos also. So, but they are not taking part in standard weak interaction, because from LEP experiment, we have bound a strong bound that there should be only three light active neutrinos which are taking part in weak interaction. So if you are thinking about these three light active neutrinos, cosmology is only telling that the sum of these masses should be below 0.2 electron volt. So the statement that you made from that table is not entirely correct, because you have to go a little bit deeper, that whether you are talking a mass of nu e or nu 1 or nu 2 or nu 3, because they are connected, right? But just take home message is that we know that the sum of these three neutrino masses should not be bigger than 0.2 electron volt at 90% confidence level if you go with lambda CDM. Okay, so those statements are not fully accurate when you go deeper.
Okay, sir. Understood.
Yes.
Thank you, sir.
Okay, there is one more question from Ritoja. Maybe the last question for this.
Yeah.
Please.
Hello, sir.
Yes.
Sir, sorry I missed, but I didn't understand where do we get this part from, that the nu e component of in nu 1 is the highest.
Yes. So for that, I need to tell you the value of these mixing angles, because I told you one thing, that what is this UE1, UE2, UE3? You see,
yes.
what is UE1? It is telling you how much nu e you need to form nu 1 mass eigenstate. Or what is UE2? It is telling you how much nu e you need to form a nu 2 mass eigenstate, right? And these are fixed in nature, and the ratio of their squares is telling you this theta 1 2 mixing angle. So when this theta 1 2 is finite, now I can tell you that the value that we know is around 34 degree or so. So from that measurement, from the oscillation data, we know that what I wrote here.
Okay.
Okay.
Yes. But
Yeah.
so this first part is established from mostly solar measurements, right?
Yes,
Solar
yes,
neutrino.
yes. Theta 1, 2 is solar, and some reactor experiment, basically Kamland also has contributed a lot. I'm going to talk about that, if you
Okay.
allow.
Okay.
Yeah.
Yeah. Thank you, sir.
Arindam, should I proceed?
Yes, please.
হ্যাঁ,
I think
অনেক কিছু আছে বলা, let's see. Okay.
okay.
So next important question, because when Biplab told me that if you can just share the glimpse of unknown territories, so the second unknown territory in oscillation physics is the mixing angle theta 2-3. This is the atmospheric mixing angle. Now, when you study muon neutrinos or muon antineutrinos from atmosphere or from lab, when you produce muon neutrinos or antineutrinos from pion decay, and you allow them to travel, what you measure in your experiment is how many muon neutrino has survived. Because I told you that muon neutrino can oscillate to other flavor. Now, if you write down that oscillation probability, that the main term in that expression is sensitive or proportional to sine square 2 theta 2. Now, the hint that we are getting from Super Kamiokande, the data that we have collected from Super Kamiokande atmospheric data, it is telling you that this quantity is around 1. Now, if sine square 2 theta 2-3 is 1, then you can immediately see we get two solutions for sine square theta 2-3, not 2 theta 2, right? So your theta 2-3 can be below 45 degree or it can be above 45 degree, right? If this sine square 2 theta 2-3 is not exactly 1. If this sine square theta 2-3 is exactly 1, then the game is over. You know that theta 2-3 is maximal, basically. The mixing angle value is 45 degree. But suppose, and this is what the data is telling now, that this sine square 2 theta 2-3, the value of this quantity is not exactly 1, but it is little bit less than 1. Now, suppose if sine square 2 theta 2-3, assume it is not 1, say 0.98. So you can immediately see that you will get two values of theta 2-3, which can give you same sine square 2 theta 2-3. One is lower than 45, which we call lower octant of theta 2-3, and another is the upper than 40, bigger than 45 degree, which we call higher octant of theta 2-3. You can say that, you can see 40 degree and 50 degree, both the values will give you sine square 2 theta 2-3 around 0.9. So this is known as the theta 2-3 puzzle or the octant ambiguity of theta 2-3. Now, I just told you, whether theta 2-3 is below 45 or above 45, you can ask me, why should I care about that? Yes, we have to care. Because that will tell you that when you form a new 3 massa against it, okay, in normal ordering, that is the heaviest one. This theta 2-3 value will tell you, you see, if it is 40 degree, then you can see that in the new 3 massa against it, you have more nu tau than nu mu. But if it is below, above 45 degrees, say 50 degree, then the nu 3 massa against it will have more nu mu than nu tau. Okay, the mu tau symmetry is already broken because we have discovered theta 1-3. But to really, establish a pattern which is deviating from TBM, which is the tri-bimaximal mixing pattern, we have seen theta 1-3 is non-zero. So we have broken the TBM pattern. But now the turn for theta 2-3. If we can measure that theta 2-3 is also not 45 degree, then the TBM pattern will be further broken. And these informations will have an important role again when you want to build your models. And I'm sure Professor Monimala Mitra, she's going to talk about all these models, mass models. And there you will learn that how crucial this mixing angle is when you build your models to explain non-zero neutrino mass and mixing. And how you can measure this quantity. So to measure this quantity, you need to rely on nu mu to nu e appearance oscillation channel. Okay. Okay. The third important question in neutrino oscillation paradigm is the question, whether the CP, the product of the fundamental symmetries, charge conjugation and parity, whether this product of CP, C and P is violated in neutrino sector, as we have seen long back in the quark sector. So as I told you that when you wrote down the 3-flavor model, you could invoke a CP phase because we are in 3-flavor paradigm. Okay. Now, if that phase is not equal to 0 or pi, then this can cause CP violation. Now you can ask me, how should I measure that? To measure that, we define a quantity called CP odd asymmetry. What is that? This is the difference between neutrino oscillation probability and anti-neutrino oscillation probability. And that is why all the current and future long baseline experiment, they deal with both neutrino beam for some time and then anti-neutrino beam. And what they are trying to measure these probabilities very precisely. And if they will see some difference, there can be some difference due to matter, right? But on top of that, if they see some difference, then you can definitely say that this difference is coming due to non-zero delta CP. So if you write down this expression for CP odd asymmetry, what you have is 4 times, this is called Yarlskog CP odd invariant. And what is that? This is basically the product of all the mixing angle sine and cosine terms. Now you see, this JCP has sine of theta 1,3, theta 2,3 and theta 1,2. So it again tells you that if any one of the mixing angle would have been 0 in nature, your job is over. The JCP is 0 and this CP odd asymmetry will be 0. And again, you can see from this expression, again, if you switch off any of the frequencies, suppose we know there are 2 independent mass square differences. So you have M1, M2, M3. Now, if any of these mass square differences would have been 0, you can again see that it will give you basically 0. You take a close look, this is 2, 1, this is 3, 2, but this is 1, 3. Okay. So to have a finite CP odd asymmetry in vacuum, this is the expression in vacuum, you need non-degenerate masses. You can't collapse these states. You need finite delta M21 square, finite delta M32 square. That's why I am writing what are the necessary conditions. You need non-degenerate masses and your mixing angle should not be 0, should not be 0 or pi. Okay. So, and mixing angles is basically, and delta CP here, if they are 0 and pi, then you are gone. So definitely delta CP has to be not equal to 0 and pi, and we are getting hints that I will explain. And you can see here that, the mixing angles, here it should be basically, 0. If that is 0, then also you are gone. And if you have 90 degree, then also you can see from this JCP expression that you will not get CP odd asymmetry. So we have fulfilled the first condition, second condition, and for third condition, we are getting hints. So let me quickly follow. So this is the global fit. So there are groups in all over the world who are doing this mammoth job for us. They are collecting all the oscillation data and then they are analyzing that in a very complicated manner. And they are telling you what is the value of these neutrino oscillation parameters now. So in this plot, which is done by these people in the reference, this is the present situation of oscillation parameters by 2021. So you can see that this blue line is for normal ordering, the red line is for inverted ordering. So in all these panels, you see you have these 6 oscillation parameters. The blue line is giving you better fit to the data compared to the red line. That means your normal ordering is preferred by inverted ordering with a delta chi-square of around 6.5. By the way, this is sigma. Okay, this is not delta chi-square. So this is the hint on this mass ordering issue that I told you. So we have roughly more than 2.3 sigma hint that in nature, maybe neutrinos are normally ordered than inverted. And you can also see that whatever ordering you take, you have a nice measurement for atmospheric mass difference. This is the solar mass difference, mass square difference. This is the atmospheric mass square difference. And now, for the first time, we are also measuring delta Cp. Indeed, I will convince you on that. And these are the values of theta 1, 2, theta 1, 3, and theta 2, 3. So here you can see, depending on which ordering you are taking, if you take normal ordering, then your best fit is coming in the lower octant. You can see my cursor. But if you go with inverted ordering, then you have a slight preference for the higher octant. Okay, so this issue of octant and the ordering is largely connected. If you need to measure either octant to tell about the hierarchy or hierarchy to tell about the octant, they are connected. Okay, so this is the value. If you want to just make a note, these are the best fit values of these oscillation parameters. And this is the 3 sigma error that we have now. And you see, this is the relative precision. So at the beginning of my talk, I told you that theta 1, 3, we just started in 2012, but we have already achieved 3% measurement on theta 1, 3. We have also very good measurement on theta 1, 2. Theta 2, 3 is little bit more error we have. And for the first time, you see, we have also 1 sigma error on delta Cp. That is amazing. This is what we have learned in last 2 years only. Believe me. Okay. So I will not have time, because here I'm showing the correlation from this paper with various mixing angles like theta 1, 3 and theta 2, 3. This is the correlation among theta 1, 3 and theta 2, 3, because both these parameters come into your expression, and you can just see that how that correlation changes when you keep adding data. In the left-hand side, there is no reactor or atmosphere data. Now you add reactor data, you see this pattern changes. Then you add atmospheric data, this pattern changes further. I will not have time. You can write to me or we can discuss offline. Similarly, you have correlation between theta 2, 3 and the atmospheric mass difference. And you see how they are nicely correlated in various data sets. This is the correlation between delta Cp and theta 2, 3. And again, how this correlation will look like depends on what data you are using. So you can see here, it is the full data set, and you can nicely see if you go with normal ordering, then your best fit theta 2, 3 is coming below 45. That means this should be in lower octant. But you see how nicely this picture gets flipped. If you go with inverted ordering, then your best fit is coming in the higher octant. And this juggling between lower to higher octant keep changing with data and with ordering. So one most fascinating thing that has happened in last 1.5 years, in 2018, I already mentioned that we measured the value of theta 1, 2 and solar mass square difference from solar oscillation data and the reactor experiment CAMLAN. Now, what is this plot, by the way? This is a plot made by these people in 2018. And you see what is the 1 sigma, 2 sigma, 3 sigma allowed range by the CAMLAN reactor experiment. CAMLAN is a dedicated short baseline reactor experiment. So you know your L and you know your reactor Newtonian energies very well. So you can measure the frequency or the splitting very well. So that's why you see the error in the measurement of frequency is very small for CAMLAN. But when you go to solar data, you have huge amount of data, but you don't know the energy precisely. That's why, and you don't have precise information on energy resolution in the detector. So you have the largest uncertainty in the frequency, but lower uncertainty in the mixing angle. Now, when you combine them, you get this much area which is allowed by both the data. But what was the situation in 2018? There was a 2 sigma, less than 2 sigma tension was there between solar and CAMLAN data. Can you see the solar based fit? You see my cursor is little bit lower in delta M square value, and the best fit from the CAMLAN is little bit higher there. Can you see my cursor? So this is the 2 sigma tension I am talking about. It was there in 2018. Now guys, you see the picture now. This year, this tension has been removed. So now you see the solar and Kamlan data, they are fitting, matching very well. And we have one best fit. And who contributed to solve this situation? The Super Kamiokande solar data of 2970 days. Okay, that helped us to remove this tension. So this is a nice plot. Yes,
Professor Agarwalla, one more. There is one raised hand from Willie. Now, if you could.
Arindam, let me continue. Jetu shomoyta kom hoye asche, and then
sure.
I will take the question at the end. I will surely take. Okay.
Sure. No
at
problem.
least let me go to some extent. So this is a nice plot prepared by my students at IOP, and here you can see that we are comparing the 3 global fit studies for all these 6 parameters. Okay, and you can see how well they match with each other and how robust is this 3 flavor paradigm. And can you see the relative 1 sigma error on these parameters? And most importantly, I want to stress, you see the delta CP. Why I am plotting between 90 to 360? Because at more than 3 sigma confidence level, we know now that delta CP cannot be between 0 to 90 degrees. And that is a remarkable progress, because that is the title of my talk. This is a remarkable progress that we have made in last couple of years, thanks to the T2K and NOVA accelerator data and the Super K atmospheric data. Now we can say at more than 3 sigma confidence that delta CP should not be between 0 and 90 degrees. That's why the landscape, the canvas has changed. The canvas is now between 90 to 360. And our job in next 10 years, how we can reduce this canvas further. You can see the best fit values, but the job of our future experiment should be to reduce these error bars. This is the nutshell, the message that I want to give you. Okay. So here is a nice slide between, if you compare the CKM mixing in the quark sector and the neutrino sector, you see we have such a big entries, when we are thinking about these mixing angles. So, and also the Yarlskog CP odd invariant, if you put the values, you see for the CKM sector, this value is around 10 to the power minus 5. But in PMNS sector, in the neutrino sector, since your mixing angles are large, that is why this value can be as large as 10 to the power minus 2. So you have a nice possibility to see CP violation in neutrino sector. So what is future? There is an experiment coming called Juno in China. This is a medium baseline reactor experiment. So they will have a 20 kiloton liquid scintillator detector. And you see, they will see, this is the detector location, and they will see electron antineutrinos from these 2 reactor sites. And the distance is 53 kilometers. And the goal of this experiment to precisely measure that neutrino issue of neutrino mass ordering, whether M3 is heavier than M1 or lower than M1. Okay. So this is the physics of Juno experiment. Depending on whether the ordering is normal or inverted, you will see either this green line or the blue line. This is the oscillation, number of events as a function of energy in this experiment. And you see, if you want to disentangle between these 2 wavy lines, the green and the blue lines, then you need a very super duper precise energy resolution, right? Because you need to really probe this much of small difference. So the energy resolution is a key issue in this experiment. I don't have time, but the slides will be there. Please take a look at how they are going to resolve the mass ordering issue. But the triumph of Juno is they are going to measure the solar mixing angle with a precision of around 0.7%. I just flashed you that, the present precision is 4%, and Juno will take us to 0.7%. Isn't it remarkable? As far as solar mass splitting is concerned, present uncertainty is 2.8%, but this Juno experiment will take us to 0.6. Amazing. And as far as atmospheric mass square difference is concerned, you see we will be improving by factor of 2 when Juno will start taking data. And you need to understand, with time, the data is becoming more and more and more precise. And when the data is becoming more and more precise, your experiments will be sensitive to any small subleading, maybe some new physics effect. Okay. So we are in a very nice stage now to ask whether we can probe some beyond standard model physics in neutrino oscillation experiments. And thanks to these experiments, they are measuring the oscillation parameters for us so precisely that now the time has come that you can ask this question, that whether these experiments will be sensitive to some neutrino oscillation itself, by the way, a BSM physics. But if you have some other BSM physics, which can come when neutrinos are produced, or when neutrinos are propagated, or when neutrinos are detected, you can ask this question. And lot of work, a plethora of work has been done or is ongoing now. You can just review the literature, okay? So the main two fundamental questions that we are asking after observing this data is why neutrinos are so light. And maybe if we answer this question, we'll get to know what is the origin of neutrinos. And another question we are asking, why quark mixings are so small compared to the neutrino mixing? Who ordered that? There is no guidance we have. So this is the well-known, the flavor puzzle. And I can assure you that you will be able to answer this question only when you will measure the PMNS parameters as precisely as at least the precision you have in the quark sector. There is no limit of precision, but at least we need to reach the level where we have the CKM precision. So what is future as far as long baseline experiments are concerned? This is very close to my heart. I am working, our group is working on various experiments, basically phenomenology. So in accelerator long baseline experiment, the main channel is nu mu to nu e oscillation channel. You also have nu mu to nu mu disappearance channel. And there are two experiments, T2K and NOVA. They are taking data now, and they are off-axis experiment. What is off-axis? You shoot a beam and you don't put your detector on axis. You put your detector a little bit off. Why? I will explain. And in future, we have Dune. This is the deep underground neutrino experiment in USA, and it will have a baseline. I'm sorry for my typo. This is 1300, not at all 13,000. It will cross the diameter of the Earth. I apologize for that. This is 1300 kilometer. But what is the difference? This is a wide band beam because your detector will be on axis compared to your flux, and you will see a wide range of energies in your detector, the neutrino energies. And this is the T2 hyper Kamiokande. This will be a detector huge in size, okay? Almost, you can say 50 times larger than the super Kamiokande detector. And they have started developing this detector. And this will be again narrow band beam because they will place their detector a little bit off to the beam direction. So in long baseline experiment, you produce neutrinos from pion decay. You have nu mu and a small amount of intrinsic nu e. Nu mu will oscillate to nu e, and you will see electron in the detector. So this is your oscillation channel, appearance oscillation channel, and you see these will be your background. You also have nu mu to nu mu, the disappearance of nu mu. They are also going to help you in measuring oscillation parameters. So this is the traditional approach of creating beams that we see in our atmosphere also. So how can I prepare a beam? This is a cartoon. You take a proton beam, you have a solid target, you hit the target, you bombard the target with proton beam, you create these pions and kaons. Then with magnetic horn, because they are charged particle, right? So they will fly apart when you produce them. So you put magnetic horn to collimate them, and then you have a decay pipe where you allow these pions or subsequent muons to decay, and you get the neutrino beam. Okay, but I want to just tell you, in T2K experiment, in NOVA experiment, which are running, and the upcoming T2 hyper K experiment, they are going to put their detector. Suppose you have some detector here, some off axis to the beam direction. Now, why off axis? You should expect that you put detector in front of your beam, right? Because you will get maximum events there. So there is a catch. These detectors put their detector off axis because you get neutrinos from pion decay. So this is an exercise I want to give you homework. You can calculate the two-body pion decay and you can land up with this nice expression. Please take us as a homework, especially for students. And you can appreciate that when you are dealing with two-body decay, you can really tune this theta, the off-axis angle, to get your desired neutrino energy for a given energy of pion. So in this plot, you can see that for a given energy of pion, suppose I am here or here, depending on where my detector is, I will have maximum neutrinos with this energy. Can you see? So suppose you want a neutrino at very low energies, then you need to go f-axis more than this 21 milliradian, and you will see that your neutrinos will they will peak at lower energies, right? So they wanted in these experiments to have maximum amount of neutrinos which are close to the first oscillation maxima in oscillation probability, and they don't want the higher energy background because they will give you neutral current background in that detector. So to improve the signal over background ratio, they put their detector a little bit off axis. So you are not eating the whole cake, but you are eating the slice of that cake. This is the off axis technique. Nova is 14 milliradian and T2K is 43.6 milliradian. And Nova's energy is 2 GeV where they peak, and T2K is 0.6 GeV. So in this experiment, this is the oscillation channel that we probe, nu mu to nu e. And you can see in this approximate expression of oscillation channel, you have so many terms, right? You have theta 2,3, sine square theta 2,3. So it tells you that it can measure the octane for you. It has theta 1,3. It has already measured theta 1,3 for us. But you can see here, it has a term with A hat. Now what is A hat? A hat is defined in this way. Now, depending on, suppose you are working with a neutrino, if you have a normal ordering, then A hat is positive. So you put a positive quantity here. But if your ordering is inverted, then A hat will be negative. And depending on, for a given new polarity, whether ordering is normal or inverted, the value of this term will be drastically different. And that will change the probability value. So this is the way you can also measure neutrino mass ordering from this channel. And you also have the Cp violating term sin delta Cp and Cp conserving term cos delta Cp. But you need to understand, this is the take home message, that when you want to learn about so many unknown parameters from one expression, you have degeneracies, right? Suppose if you have two unknowns and you have one equation, can you solve it? No, you will get degeneracies. You need at least two equations to solve two unknowns. So in our language, what will be the two equations? Two equations means two experiments, two different experiments. Two different experiments at different energy and baseline. And when you combine their data, they will break the degeneracies. And this is exactly what is happening with T2K Nova. I don't have time to explain these plots, but this is a plot I am showing where you can see how much matter effect you have in these present and upcoming experiments. And these are the location of first and second oscillation maxima. So in these experiments, you can see we have at most 5 to 10% matter effect. Okay, because your baseline is not very large. Maximum baseline that we have is around 1300 kilometers, right? So you can see here that this is the amount of matter we will have. That means fake Cp asymmetry in these experiments. So this is the Nova experiment, and this is the Nova, and this is the T2K experiment. The job is let them run, let them collect data, and you combine the data and you measure the value of Cp phase and other issues. So what is the T2K data now? So this is the data from T2K experiments. I will not go in detail. I will be sharing these slides, so please take a look. And this is the data from NOVA, because I have already given you the summary of what we have learned globally from all this data. So I'm not going one by one. And this is the future Dune experiment. And from their analysis, they have convinced us that when this experiment will come online and they will shoot a beam from Fermilab to South Dakota with a baseline of 1300 kilometers with a wide band beam, they will have CP violation. They can assure us that they have seen CP violation for 50% values of the CP choices at 3 sigma confidence level in 5 years and at 5 sigma confidence level in 10 years. So we are confident, and if we are lucky, if delta CP really turns out to be around minus 90 degree, then the job for this experiment will be easier, and they are going to establish that they have CP violation at more than 5 sigma confidence level with just 3 or around 4 or 5 years of data take. So we have a very good opportunity lying ahead to see CP violation. And since you have 1300 kilometer, it is mentioned that you can measure the mass ordering in less than 2 years at 5 sigma confidence. And what about T2 hyper K? So this is the physics results, or expected results from T2 hyper Kamiokande experiment in Japan. They have started the construction of this detector, and this is, you can see, almost huge. Super Kamiokande is 25 kiloton fiducial, and this is 6 times more than that. Its fiducial is 188 kiloton. So you can see what a big jump we are going to take with this hyper Kamiokande detector. And they also have a very good CP violation sensitivity. Remember, the major difference between Dune and hyper Kamiokande, T2 hyper Kamiokande, Dune baseline is large. So you have matter effect that helps you to measure neutrino mass ordering. I just explained. But T2 hyper Kamiokande, the baseline is again 295. So you don't have matter. So you have a clean base to measure CP asymmetry without bothering about phase asymmetry. And also T2 hyper Kamiokande will use a narrow band beam, but since Dune will use a wide band beam, you can also probe first and second oscillation maxima quite well, and that plays an important role when you want to measure the value of CP phases. Okay, so this is the landscape of Dune and T2 hyper K. I don't have time to just go beyond, but Arindam, I would like to take just 5 minutes more because there are so many questions. I just want to tell you that there are some practical application of neutrino oscillations when neutrino travels in matter. So this is a cartoon of our Earth core, right? We know that roughly there are 3 layers. There is a core, there is a mantle, and there is a crust. Now, from earthquake studies, from seismic studies, we have a very good idea about our Earth structure. And there we have roughly these 3 layers of Earth: core, mantle, and crust. Now, I want to assure you that if our own experiment, India-based neutrino observatory, if they will collect atmospheric data, and this detector will be magnetized, so you can observe atmospheric neutrinos and antineutrinos separately, because nu mu will give you mu minus, nu mu bar will give you mu plus, and you have magnetic field detector, so you will see that they are bending in different directions. So if this experiment will come in our country and they will collect atmospheric data with a 50 kiloton detector in 10 years, I want to assure, this is the work that we have done recently, that with that data can tell you that yes, indeed, there is a core inside the Earth. So isn't it very fascinating that you are going to validate the presence of the core inside the Earth from a new source, from a new method, and which is neutrino oscillation inside matter. I told you, when these atmospheric neutrinos will pass through core, they will feel the core through matter effect. And they will tell you whether they have seen matter or not, because when you go from mantle to core, so you see, we have constructed various profiles here, And we are trying that when we will have data, which model will fit the data and which will not. So in this paper, we came up with a coreless profile of the Earth, which we say mantle crust. So we are assuming that there is no core. Let the data reject it. That is the game of this study. And you see, I will not go into details, but just remember, if this ion experiment will come, which we hope, in 10 years, they will see almost 331 mu minus events, which are indeed passing through core, and 150 odd mu plus events. And they will tell you that there is a core. And if we will collect this data, we will be able to reject the coreless mantle crust profile around delta chi-square of 7.45. So this is a fascinating study. You know, you can see apart from our enhancing our knowledge on basic research, neutrinos do have fundamental application, basic application, practical applications. So with neutrino tomography, you can penetrate your Earth and you can scan your Earth. So this is just a glimpse, and this area is flourishing. A lot of study can be done along this direction using neutrinos, which are passing through the Earth, inner layer of the Earth. Okay, so just one more minute. I didn't get time to explain or tell you that these experiments will be also a nice tool to probe BSM physics. I told you that neutrino oscillation is already beyond the standard model. But now, with time, the oscillation data is becoming precise and precise and precise. Your experiments are becoming bigger, bigger and bigger. Your systematics are becoming lesser and lesser and lesser. So everything is happening positive. So then it is the right time you can ask that what if there are some new physics is hanging around, can this data be sensitive? So in literature, people have explored a lot of possibilities. I don't have time again, but you see, these are the candidates. You have starting from non-standard interaction, presence of sterile neutrino, interaction of neutrinos with dark matter, extra dimensions, supersymmetry, leptoquarks, monopoles, decay of neutrinos, decay of dark matter. You have plethora of possibilities. And when you do neutrino experiment, these new physics can affect your neutrinos at production. These new physics models can affect your neutrino propagation. And these new physics effects can affect your neutrino detection. That means the detection cross-section. And with high energy astrophysical neutrinos, by measuring the flavor ratio with these four observables, by measuring the energy spectra, by looking at the arrival direction, by measuring the flavor composition, and by measuring the arrival time, you can really disentangle that which new physics is there in nature. So we did some work. I'm not going to make a publicity of our study. You can just take a look. So here I come to my concluding slide. I apologize that I had to rush because of time lack, but what I tried to convince you in last 1.5 hours, that we have a rich fundamental physics that you can learn with the help of neutrino oscillation experiments. It seems that this oscillation is very simple phenomena. That is the beauty of oscillation. It is simple, but at the same time, it is robust. And it can give you so many information about our universe, about our fundamental science. I want to just convince you, we never asked in our life, why should we measure the mass of electron? Because we started our life with mass of electron. That was the first fundamental particle that we discovered and measured the charge and the mass of that electron. Now I want to convince you with my concluding slide that the oscillation parameters that I just talked about you, they are not a science fiction anymore. They are reality. It is our job to accommodate them in standard model. Thanks to our experimental friends and the people who are also doing phenomenology, because they have analyzed the data so well. So this is not anymore science fiction. You have these 6 parameters. And I can tell you that these are as fundamental as the mass of an electron. So as a physicist, this is our job to come up with more better and better experiments and measure these fundamental parameters. And I strongly believe that nature is very beautiful. It is simple, but it has so many things to offer you. So similarly, neutrino oscillation is very simple, but it is so robust. And I explained to you that present is very exciting. I just showed you what we have learned in last 3-4 years. There were tensions, but with more data, tensions are relieved. There is a tension now between T2K and NOVA data, but my hardcore feeling is this tension will be relieved when we'll have more data from NOVA and T2K. And I also assured you that the neutrino future roadmap is very bright. We have long baseline experiment, Dune and T2 hypercamioconde. Juno is just going to start. We will have in our country, India-based neutrino observatory. All these big detectors will collect atmospheric data. They will also see solar neutrino data. So we will have plethora of data, ample of opportunities. And I am sure in next 5 years or so, exploring BSM will be the highlight of neutrino oscillation physics, because by that time we will have sufficient information about these neutrino oscillation parameters. So guys, stay tuned and just explore this beauty with neutrino oscillation. Thank you.
Thank you, Professor Agarwal, for the excellent presentation. We have a few questions. Wilina, you would like to ask now? You could unmute yourself and ask the question. Are
Yes,
you around?
please.
Okay, maybe not around. There are 2 questions in the chat box. First, maybe Sabila, you would like to ask the first question?
Yes, please.
Am I audible?
Yes, you are audible. Please.
Sir, could you please repeat again why we are putting a detector a little bit off in the
Yeah, very good question. What is your name, by the way?
Sabila.
Okay, so let me explain to you. Very good question. I'm glad that I was rushing like hell, but you are focused. Good. So, see, in any particle physics experiment, our main goal is to enhance our signal rate and reduce your background. Because when you do experiment, you just collect data. And you can't tell that data itself can't tell you that, okay, look, I am a signal, I am a background. You have a Monte Carlo, you have a, Monte Carlo simulation to, just tell you that, okay, this looks like more data, this looks like more background. So the first message is, this is always, we want that we should reduce our background and we should enhance our signal rate. Now, when T2K and NOVA, they were proposed and planned, it was when I was just starting my PhD, okay, in 2004 or 3 end. That time they were discussing, okay, we will have this experiment. So that time θ13 was not discovered. We had only an upper bound that θ13 can be 12 degree or less. Less means 0 is also allowed. Now I told you with this expression, if θ13 would have been very small or 0, then the probability that nu will oscillate to nu e in T2K and NOVA will be basically 0. But you are using taxpayers' money and building such a big experiment. So you can't take risk. So they thought, okay, so let us think that our luck will be very difficult and θ13 will be very small, suppose. If it is big, well and good. But if it is small, then your signal rate will be very small. So you can't have the flexibility that you can have huge number of background. So first, kill your background, okay? That is the first lesson. So how they kill the background? So they create a neutrino beam. Suppose you are at J Park or you are in Fermi Lab, You hit the proton with a target and you create pion and they are decaying. Now, pion decay is a two-body decay. I'm sure you have learned in this school, or you just open any textbook, Haljan Martin, or any particle physics textbook, you will see you can calculate two-body pion decay. Why don't you take it as an exercise? So when you have a two-body decay of pion, you can land up with this such one-to-one correspondence between theta. Theta is the off-axis angle. So when neutrinos are emitting, you don't have any handle on that, right? They are emitting with various energies at various angle and they're flying. Now it is up to you. If you put your detector on axis, just right in front of your beam, you will see this black line, this relation. That means for a given pion energy, you will have this much of neutrino energy basically. But suppose your baseline, T2K baseline is 295 kilometers. And you can calculate with a two-flavor formula that for 295 kilometers, the oscillation maxima, where you expect maximum nu mu to nu e transition, that will be 0.6 GeV. So especially for students, I have a simple task for you. At the beginning, I showed a two-flavor formula of nu alpha going to nu beta. Can you please calculate, take L 295 kilometer, take delta m31 square is the atmospheric mass splitting 2.5 10 to the power minus 3 V square, and you want that oscillation phase to be maximum, means pi by 2. Take pi by 2. So 1.27 delta m31 square L by E is pi by 2. You know L, you know roughly delta m31 square. You calculate E for T2K and you will get this will be 0.6 GeV. So they had this understanding that they want only neutrinos which are peaking at 0.6 GeV. Now please see this plot. For T2K, they put a detector not on the line but little bit off, 2.5 degree off, which is 43.6 milliradian. Means this is for 21, but if you go further off, you see this curve will like this, which I am not showing here, and it will be peaked. It will be peaked for at around 0.6 GeV. So depending on your pion energy, but you can see when you go off in this plot, you peak at lower and lower energies. Can you see this peak is here? When you go further off, the peak is here. When you go further off, the peak is here. So you have neutrinos emitting in all possible directions with all possible energies, but putting a detector off axis, you are just looking at those neutrinos which are relevant for you, which will give you maximum nu mu to nu e oscillation. That means all other high energy neutrinos, these neutrinos, they are not coming in your detector and they are not also going to give oscillation. So they will not contribute to signal, but they can make your life hell. They can give you so many backgrounds. So to cut that background, you don't want those neutrinos to arrive in your detector. So you are hiding your detector a little bit off. Okay. So this is the classic kinematics, just simple kinematics of two-body pion decay. Guys, please do this exercise. Okay. And try to appreciate that these experiments, when they are not sure that θ13 is large, now we know that it is 8.6 degree, but it was planned in 2002 and they were not sure what is the value of θ13 would be. So they wanted to maximize the signal over background ratio and they adopted this off-axis technique. Okay. I'm not sure whether it is clear to you, but if it is not clear, first do this exercise and you can come back to me. You have my email address, write to me, call me, anything, and I'll be happy to spend hours and hours to explain this to you.
Yeah, I got it, sir. Thank you so much.
Okay, good.
Thank you. Next question is from Radhika. Due to lack of time, maybe we will take just this question. And Sanjita, is it okay if we collect the questions and send it to you?
Yes, yes. Arindo, you can do that, please. because the
Sure.
purpose is
I
to
see
help-
several raised hands, about 4 raised hands, and one more question in the chat box. Due to lack of time, we may not be able to take all of them. So
yes, or you just collect it, send me, or tell them to contact me. Write an
sure.
email. Yes.
Thank you. So Radhika, if you could ask briefly, you can unmute yourself and ask.
Hello, sir. Can you please explain the fake CP asymmetry again?
Okay, very good. So Radhika, the situation is the following. Whether you take any experiment, T2K, NOVA, Dune, T2 hypercamioconde, right? These experiments, or atmospheric experiment. These neutrinos, they don't travel in vacuum, right? This in the terrestrial experiment. So they passes through matter. Now I explained in detail this matter effect. So in matter, you have only electron, but you don't have positron. Okay? And you also don't have muon or tau. So when a NUI will go through matter and you have only electron, they can interact via charge current process. And NUI can also interact, NUI bar can also interact with electron because there is no positron via same charge current process. And if you calculate that what is the potential means you can think like it is like your JWKB approximation, okay, in quantum mechanics, advanced quantum mechanics. Like, you started with a car from your city to say Bhubaneswar, and on the way you are just, sitting in the car and your car is moving. But on the road you have so many bumpers, right? So your car was in a right condition at the beginning, but when you reach at the destination, you will see that तुम्हारे car का एक पुर्जा खुल के गिर गया. Okay. So here also it is like, light passes through medium, or light passing through glass. Similarly, neutrinos are passing through matter, and when they are interacting with the ambient electrons, there will be many electrons on the way, right? And there will be forward elastic scattering. It will be elastic. So neutrino energy will not change, and it will be coherent and forward. So you can sum the effect, and at the end you will get a net potential. Like neutrinos will have an effective mass, you can say. Okay, but that amount will be different for neutrino and antineutrino. Now I told you that to measure the CP phase, the plan is you measure the neutrino oscillation probability. Suppose you are building a neutrino beam in Fermi lab and you are shooting it to South Dakota. Neutrinos will pass through 1300 kilometers in the earth. You shoot a neutrino beam and you shoot an antineutrino beam. Measure the probability in your detector. Now, if you see that these probabilities are not same, you can say, okay, so what goes wrong? One answer is your U has become U star because you have delta CP. U is a complex quantity, right? So U has become U star, delta CP has gone to minus delta CP, and that is why you are seeing this difference. So you are very happy that, okay, let's measure the difference, and then by fitting, let's estimate the value of delta. So this difference will be, if it is happening due to delta CP, is the genuine CP asymmetry. CP asymmetry is nothing but the difference between neutrino and antineutrino oscillation probability. But I told you, there is a problem. When these neutrinos are traveling from Fermi lab to South Dakota, there is matter. Oh my God. So this matter will act differently for neutrino and antineutrino and will give rise to different potential. For neutrino, it will be positive, and for antineutrino, it will be negative. Now, I showed in my talk that this matter comes into the probability expression. So you have to be very careful. So if this A is non-zero, then this can also create difference between neutrino and antineutrino oscillation probability. And that difference, this is not caused due to delta CP, but this is caused due to matter. So the asymmetry that is you are seeing because of matter, you can call it, sir, this is not genuine CP asymmetry. This is my fake CP asymmetry. But come on, you have one data and everything is jumbled up there. I showed you the expression, right, of probability expression here, that everything is combined in this picture. So the job for the current and future experiment, how to separate that I have this much net CP asymmetry, but this much due to delta CP, this much due to matter. And that will not happen, or that is not possible with one experiment. This is possible if you have experiments at different energies, different baseline. Like if you have experiment with T2HK, there is no matter effect there. The baseline is 295. So you can just measure the genuine CP asymmetry. But you need to know mass ordering. You need matter effect. You go to Dune. Dune with matter effect, it will tell you what is the ordering of the neutrino masses. And if you combine these two data, you will be able to resolve your CP issue with more precision and unprecedented level confidence. So this is the issue of fake and genuine CP asymmetry. Fake asymmetry comes due to matter. Remember, because your matter is not CP symmetric, you have only electron in the matter. There is no positron. Antimatter nahi hai. And the genuine CP asymmetry happens due to the genuine Dirac CP phase that is sitting in your model with theta 1. Does that answer your question?
Yes, sir. Thank you.
Okay. So let us thank Professor Sanjib Agarwalla for this excellent presentation and for enlightening about neutrinos.